the only thing I wanted to tell you.
Okay. Okay, hocam.
Ali Hocam, you started recording, I think, already.
Yes, I started. If everyone ready, I think we can start. Now it's 1 o'clock.
Yes, please. It's 1 o'clock. We can start now.
Is everybody
So if-
ready? I think everybody ready, probably.
If my
Yes.
camera is not a problem, I mean, if then I am ready as well.
As long as you see the screen and as long as you follow the seminar, there's no problem, Hocam.
So,
Hocam, only close your camera that your picture will be casted if you close it.
okay. That is it. Okay. So,
Yes.
Yes.
That's
wait,
that's great.
camera.
That's it.
That's
Okay.
fine.
Yes.
Yes,
Yes.
fine.
Hocam.
Thank you very much.
Okay.
So let's get started. Okay, Yashmitha. Okay, the stage is yours now. Go ahead.
Okay. Thank you, Ajam. Respected members of the jury, respected faculty members of Eastern Mediterranean University, my dear family and friends, welcome to my thesis defense presentation today. And it's an incredible honor to be presenting today for my PhD degree. And my title is Weak Gravitational Lensing via the Gauss-Bonnet Theorem. And I have been working since 2019 under the supervision of Associate Professor Dr. Ali Yovkyun. So this is my title today, and I'm going to move on to the next slide. So this is a short summary of the publications I have done during my PhD. I have 5 publications, and I have 1 under review right now. These will be the topics that I'll be presenting today as well.
Yashmitha, sorry, but here with our title, you write with deflection angle via Gauss-Bonnet theorem. If you want, you can correct it quickly.
Okay.
It will be same, but
This one here?
In the
Okay.
first page.
in the first page, yes.
Not a big error, but just to be correct.
Okay.
Thanks.
Okay. Is that okay now, Ajam? Are you still able to see my screen?
No, we don't see your screen yet. Maybe
Okay.
you're gonna share.
Let me share again. Okay. Is it visible now?
Okay, yeah, that's correct. Everything is right now.
Yes, it's okay.
Okay. So this is a brief summary of my profile as on Google Scholar. And this is my overall publication history. So I plan to work in this line as well. And this project, this research that I have done will be based on the first 5 publications in this list. So these will be the contents of today's presentation. I will be introducing some fundamental theories that I have been using for my research, mainly the Gauss-Bonnet theorem. And then I will proceed to explain how I used it in the AUP black hole, then the asymptotically flat black hole in Hornetsky theory, then a Hornetsky black hole, then the RN black hole, and followed by the AMC-NS black hole. So I would conclude with a brief summary of all the results and the scope of this research in the future. So the first introductory topic is gravity. I would like to start all the way from gravity as one of the 4 fundamental forces, and how Sir Isaac Newton discovered gravity through an apple. Because this is one of my favorite analogies, or it's a famous moment in history, and it's an inspiration for me personally, because there is a saying from said Baruch that says, so many people have seen an apple fall from the tree, but Newton was the only one who asked why. So I would like to ask questions like that, and that is why this kind of research is very interesting for me. So according to Newton, gravity is a force that attracts two masses that are separated by a distance. And his theory, although it was sound at that time, it did not account for various gravitational effects and the missing mass problem and so on. So we had to come up with some modifications, which will be discussed in the further slides. And Albert Einstein proposed in his theory of relativity that gravity is rather the curvature that is found in the fabric of space-time due to a mass. So then this theory, it actually answers the existing questions and more, which were surprisingly consistent with observations, making the theory more and more sound. Then I would like to talk about black holes a little bit. So like we said earlier, gravity is one of the fundamental forces. Also, gravity is the weakest force in the universe. So gravity is weak until the mass of the gravitating object starts increasing. And as it increases, we have a black hole in the extreme gravity area. That is what is the essence of this project. And a black hole is an object of extreme gravity that is with infinite density that is concentrated on a single point, collapsing on itself and crushing all the forces and making all our theories redundant. So according to GR, there exists regions of space, and these regions have so much pull that even light cannot escape. But these are the standard definitions that we have heard like everywhere that defines black holes. Then further, because of these regions that collapse due to its own gravity, we have singularity in its center, where none of our physics that we know of today does not stand. So this is surrounded by a boundary called the event horizon. And as in this picture, we see an event horizon beyond which we have no information whatsoever. And then we have the ergosphere, where the space-time is still bending enough to know to feel the extent of the black hole's gravity. And then we have the quiet region where the gravity of the black hole is no longer prominent. So Einstein, Schwarzschild, Kerr, and so many others have given their works to help us understand black holes. And these works have been confirmed 100 years later by LIGO and EHT with their observations of gravitational mergers and the Event Horizon Telescope project. So a dying star with a mass at least 3 times that of the sun becomes a black hole, according to the Tolman-Oppenheimer-Volkoff limit that was derived initially from the Chandrasekhar limit. So that is the minimum amount needed for any dying star to become a black hole. So this is a summary of the history before Einstein gave his theory. Starting from Newton, we have do not bodies act upon light at a distance and by their action bend its rays, and it's not its action strongest at the least distance. And from there, we have Cavendish, who calculated the deflection angle in Newtonian gravity, followed by von Soldner, who gave the 0.84 arcsecs that was too small to be relevant. And then in the 1800s later, we have wave theory that was favored against the Cavendish theory, corpuscular theory. And then after that, we have Einstein, who says that geometry theory of gravity would actually exhibit light deflection, although wave theory does not cover that, and the deflection angle agrees with that of Cavendish's value. And then finally, Eddington is the one who did the ultimate theoretical and through experimental transition from the 1919 eclipse in the island of Principe and Brazil. So he measured the deflection of the sun to be 1.61 plus or minus 0.3 arcseconds. And we can see the news that made the headlines from 1919. And here we can see Einstein being mentioned and his works being mentioned because of Neptune's missing mass problem. So all the way from 1919 to 2019, we have 100 years of research that tell us theoretically what all we know, just a bunch of theoretical equations and mathematics. But when we looked into the sky through the telescope, we were actually able to see that the black holes were real and they do exist. And it's just amazing to know that we are going the right direction to understand the universe. So the next question is, we have gravity. So is the gravity around a gravitating object so strong that it can bend light? The simple answer to this question is yes. And that we call the gravitational lensing. So a black hole is surrounded by an accretion disk in which matter, dust, and photons are stuck in unstable orbits around it, and they have absolutely no way of escaping those orbits. This not so circular photon sphere gives rise to the bending of light due to gravity. And this phenomenon is known as the gravitational lensing. And it is classified into strong lensing and weak lensing. So we have gravity that bends the path of light. So for a star, we can see that it's pretty straight in comparison to a white dwarf, which is slowly curving, and a neutron star, which curves even further, to a black hole, where it is stuck in an orbit that it can never escape. So this is the pictorial representation of Eddington's observation, so 1.75 arcsecs, and this is the actual position of star to the apparent position. And this is a representation of how gravitational lensing occurs from the source through the lens and to the observer. You can see the space-time fabric is bent, and so the light appears to be bent because its trajectory is bent. So in this research, I'm explicitly interested in weak lensing because it is a consequence of general relativity that arises from very minor distortions that are very, very small to be detected, but are just enough to distinguish between mass distributions. So it possesses this subtle property of differential deflection. That is, it's the bending of light that enables the exploration of cosmic structures deeper in a way that is differentially zoomed because of its action as a lens. So the angle at which the bending occurs is called the deflection angle, which is what I'm interested in. And the final topic for the introductory portion is the shadow of a black hole. So the thin accretion disk that we discussed above, plus the lensing effect, gravitational lensing effect, together gives the appearance of a shadow for a black hole. And it has an emission region that is geometrically thick but optically thin, meaning that it has a disk that is thick across the geometry, but the matter around the disk is pretty scarce, meaning that light passes through it without being scattered much or absorbed in any form. So that means it's optically thin. And it is accompanied by a distant, homogeneous, isotropic emission ring, and that is what we see as the shadows. When we think of a shadow of a black hole, all we can remember is the first image, at least that comes to our mind, is a black center surrounded by a bright surrounding. So that's what it is. And it is defined as the critical curve interior, separating the capture orbits that go into the black hole from the scattering orbits that swerve away. So there are some orbits that are into the black hole that are stuck to the black hole forever. And there are some that are spiraling away and coming towards the observer because of the scattering. And that is the curve, that's that one curve that separates these two orbits. So the entering versus exiting photons is what is the shadow. And we will be discussing that as well. So for the Event Horizon Telescope's picture, we have the observations here, and we have a fine-tuned observation here because of the machine learning technology. And we can see that it has become sharper. And we have the accretion disk that is visible. So the accretion disk formed from the black hole's gravity determines how the shadow looks to us. So it's attracting and trapping everything in its path, dust, photons, and radiation. Its size depends completely on the black hole, like say mass or spin, whatever. And then we have its contour that is determined by its orbital instability. So the more unstable photon orbits, the more dynamic its contour is going to be. The contour is dependent on the light rays from the photon sphere, and that makes it appear to be a dark two-dimensional disk for a distant observer. And it's, of course, illuminated by its bright uniform surrounding. So now that I have established all the basis of my research, this is the aim of my research, to devise new theories with the help of existing theories that are being proved through the observations, and to give and find ways theoretically that enhance the parameters that limit the current technology, like the black hole picture, shadow picture we just saw. So someone made that enhancing of the parameters to make that happen, and I wish to do something similar, and to propose corrections or hypotheses that will aid observational astrophysics to come up with more amazing observations, and to extrapolate the understanding we have of the black holes and improve on it by reducing the number of assumptions. So the more theories that we have, sometimes they get rejected or they get modified because of the number of assumptions, and I want to minimize the number of assumptions in my research. And of course, to contribute to the study of the cosmos that inspires other scientists of now and the future. So the first topic that I will be discussing right now is the Gauss-Bonnet theorem, which is the fundamental foundation of my research. So the Gauss-Bonnet theorem relies on the fact that the deflection angle can be calculated outside the light rays domain. So we do not even have to include the black hole singularity as a factor to calculate to use the Gauss-Bonnet theorem. It uses the subtle property of differential deflection that we spoke about in weak lensing. And it gives a relationship between the geometry and the topology. Since there is curvature that curves the space-time that is involved, it involves geometry. We have to find a theory appropriate, such as the Gauss-Bonnet theorem, because it gives a relation between geometry and topology. So this is the relationship in mathematical form, and the corresponding names of the parameters are given on the right side. And for the space-time geometry, this is defined as ds square here, that is defined here as this curved line, the line element that joins the two extremes of this space-time fabric in the curvature. So next we have the ds square in the more in the four-dimensional metric form, and d is chosen, as we saw, as we can see here, in the region in the equatorial plane, with theta is equal to pi/2 taken as a solution of the optical geometry to apply the Gauss-Bonnet theorem. So for an asymptotically flat space-time, source and observer are very far from the black hole, which is not surprising. And D is just a region that connects the light and source through two different ways. One as the smooth curve here, and one as the light ray that is bent here. So the boundary, the partial differential of D, is generated by the smooth particle, and we have the unit speed condition because of the smoothness of the curve. Here we have gamma here that has unit speed vector and the unit acceleration vector given by this deflection there, and a circular curve arc connecting the source and observer. So the central black hole is located outside the domain of D, as we said earlier, and the space-time singularities are excluded from this region. So this next portion of this is the Gibbons and Werner method, which is further simplifying the Gauss-Bonnet theorem for the given domain. So it reduces the complexity of Gauss-Bonnet theorem. Source at infinity is viewed by the observer in an asymptotically flat space-time through a mass distribution that exhibits spherical symmetry, and this is the initial case. And the black hole functions as the lens between the source and the observer. So the optical geometry can be obtained from the four-dimensional black hole space-time by imposing a null constraint to the spatial geometry. So Gibbons and Werner gave that in optical geometry, ds square is equal to 0. We have that dt square can be taken as the optical geometry, and the deflection angle can be calculated as such. So for the smooth curve in domain D, we have optical curvature with unit speed and unit acceleration vector. We have the optical metric as 1. So this equation, the same Gauss-Bonnet theorem equation, the inverted form is written here. So I'm going to analyze each term individually. So the Euler characteristic connects the geometry and the topology to the structure, defined as faces minus edges plus vertices. And we have Euler characteristics for this domain as 1. So 2 pi psi d is 2 pi. Then we have the exterior angles, sum of exterior angles taken for each discontinuous point in D. So we have two exterior angles here, theta 1 and theta 2. And together, according to this geometry, we can see that it is equal to pi, giving that together this term and this term gives pi. Then the third term, the geodesic curvature, measures the curvature of the curve on a curved surface. So how much a curve curves is what it measures. And we have the formula here for this smooth curve, and that reduces to, in this curve alone, it reduces to 1 over r times r d phi, and which can be equated to d phi. And finally, putting all this together, we can find that if we integrate it from 0 to alpha, pi plus alpha hat, we can see that alpha hat is equal to negative of Gaussian curvature times the area of the domain in question. So this alpha hat here is known as the weak deflection angle. So the Gauss-Bonnet theorem, written as this, can give the deflection angle according to Gibbons and Werner as a very small quantity here. It's reduced. And this strongly depends on the mass of the enclosed body, as one can expect. And one more thing to notice here is that it is negative. It has a negative sign. So k less than 0 means that geodesics must locally diverge when we are calculating. So I would like to start the methodology of the research with the Schwarzschild black hole in vacuum. So the function of the Schwarzschild black hole is given as 1 minus 2m over r. This is a lapse function given here. It's to show the behavior of the function with varying mass. And then the line element is written according to the earlier defined metric. It's written as this form. And the Christoffel symbols are then calculated for this line element to find the Ricci scalar. So the Ricci scalar divided by 2 will give us the Gaussian curvature. And using the straight line approximation, r is equal to b over sine phi, where b is the impact parameter, we can find the weak deflection angle of a Schwarzschild black hole to be 4m over b. So ds here is simply r dr d phi. It's just a simple term here that can be found from the normal geometry. And the impact parameter is actually a variant of the light ray. It's an invariant of the light ray, and it's a constant of motion. And its perpendicular distance, it's defined as the perpendicular distance from the center of the black hole to the tangent of the light trajectory to the observer. As we can see in this picture here, you can see that there should be a tangential line that joins it. So to be depicted here, you can see that deflection angle is this angle here. So for a Schwarzschild black hole, in vacuum, we just defined the deflection angle for a massive particles. For a Schwarzschild black hole surrounded by massive particles, we find the Jacobi metric using the circular photons orbit at theta equal to pi by 2 as e square minus m square. So naturally, an asymptotic observer perceives one of the conserved quantities as energy. So meaning that if m is equal to 0, energy equal to 1. So that essentially reduces it to the normal dt square, meaning that the quantity is defined for a photon. So Gaussian optical curvature becomes this factor here, and we have again straight line approximation at the equatorial plane to give alpha hat as this term here. So next we talk about vacuum medium. Since we were talking about vacuum medium so far, we will talk about medium in general. So we have the Einstein angle given by Einstein that was discussed earlier. And deflection angle of a photon in vacuum does not depend on photon frequency or energy. So deflection, and hence gravitational lensing, is achromatic, meaning that it travels as one ray of light. But in the presence of medium, it significantly alters the dispersive characteristics of a light ray. So in the presence of plasma, let's say, what happens is as matter falls into a black hole, it collapses, it heats up, and it reaches millions of degrees, and it forms active plasma. So in outer space, light rays travels through these hot ionized soup of plasma, and these photons undergo various effects. And that one major effect is seen in the deflection angle when the black hole is surrounded by plasma. And due to the properties of plasma, chromatic effects are expected to rise. So for lensing, the main interest is the change in the deflection angle of the light ray. Refraction means that when a light ray strikes this heated mixture of ionized gas, there is refraction, implying the presence of a refractive index factor. So we will find refractive index for our calculations of light rays to a black hole surrounded by plasma. So this refractive index factor reveals an essential component that contributes to the bending angle. Light rays in a transparent homogeneous medium propagate along curved trajectories, and this is not related to gravity or relativity. It occurs only if the medium is optically non-homogeneous, naturally, and the refractive index is defined as a variable or a function of x, let's say. So mathematically speaking, when surrounded by any media, we have refractive index defined as velocity of speed of light over velocity of the mass particle or any particle. So we have the line element, the optical line element here defined as this with the refractive index. And we have omega e squared to omega infinity, the ratio here as n here. So n here is the ratio of omega e over omega w infinity. So for a Schwarzschild black hole in plasma medium, we have 2m over b times 1 plus 1 over the refractive index factor. This is the n square that we have here. So together we can see the effect of plasma as a separate entity here. And finally, the dark matter is also analyzed. So invisible form of matter makes up most of the mass in the universe, and we have a big proportion of 5% is visible matter, rest of it is dark matter and dark energy. So it creates its underlying structure of the universe. So its gravity derives normal matter to collect, building up into stars and galaxies. Though dark matter is an invisible material and cannot be seen, it still accounts for the nature of the placement of lensed objects, and it affects the deflection angle. So we will be talking about that as well. Here we can visibly see the effects of distortion and weak lensing due to dark matter, image courtesy of NASA. And then refractive index defined for dark matter is given here. For B, which is a factor of density proportional to density, and we have U, and that is a factor proportional to the scatterer or charge. So together we have the weak deflection angle for a Schwarzschild black hole as this. So I would like to bring attention to the graphical nature of each of the deflection angles we just discussed above. This is for the vacuum case. We have the least case of 1 mass here, and as we increase with number towards 2, we can see how much the deflection angle increases. So I would also like to pay attention to the y-axis, because it will be different for each of the following black holes that we will discuss. And then we have the effects due to the massive particles, and that we can see that the more v increases, that is the velocity of the massive particles, the lesser the deflection is going to be. And then we have the plasma medium, the more the refraction, more the deflection. And then we have the effects of dark matter medium. More the dark matter, more the deflection. And we can see that it is massively different from the right plot. So this is the methodology, and the next topic is to apply these 4 effects onto extended uncertainty principal black holes. So we will call that EUP black holes, and the basics for this is information paradox. It's a fundamental puzzle, and this was proposed by Hawking as a solution that the dissipation of matter was happening through quantum fluctuations, and that the information is never actually lost, it's still there. So as a quantum entity, black holes were related to Heisenberg's uncertainty principle. And because of this, we have the generalized uncertainty principle, which prevents the black hole from dissipating as per Hawking's proposal. So this includes an additional term mathematically in the Heisenberg relation, and it is proportional to the square of momentum uncertainty. So we know the Heisenberg uncertainty principle as the uncertainty in position times the uncertainty in momentum is a direct constant. So we have that to help us here. And since general uncertainty principle talks about momentum uncertainty, we have the alternative form, the extended uncertainty principle, which talks about the additional term that is proportional to the square of the position uncertainty. So we have the general uncertainty principle from the Heisenberg's uncertainty principle, and we just have this extra term here. It's alpha times delta x square over L square. L is the fundamental distance often perceived as a Planck length, and alpha is a coupling constant, which is actually the constant that we will be using, as we can see later. So for the function fr for a EUP black hole is given by this form. So we can see that 1 minus 2m over r here is the Schwarzschild case, and we have the EUP factor here. So with alpha equal to 0, this reduces to the Schwarzschild case. So this is the lapse function for each of the quantities, changing alpha, changing L, and changing m. Although the nature is same, we can see that they are mildly different from each other here and quite very different here. So these lapse functions we plotted to choose an appropriate value for the calculations. So the weak deflection angle in vacuum medium is this. So we will follow for the plasma medium. We have refractive index defined as this. We have 1 minus the ratio of frequencies times f of r. Then we will have the deflection angle given to be this equation. And naturally, we have alpha equal to 0 reduces to Schwarzschild case. So these two terms here, we can see that it gives us this 2m over L factor, which can be interpreted in the post-Newtonian approach. Then we have, again, of course, we have a refractive index ratio. The ratio of frequencies to 0 means it reduces to the vacuum case. So the adaptability of the equation is noteworthy here. The next we want to see the variation of deflection angle with respect to the impact parameter. We can see that for alpha is equal to 0, it's the general Schwarzschild case. And for alpha is equal to 0 and refractive index for the same Schwarzschild case. And then we can see how deflection, although it looks small, in the left side on the y-axis, if we see, we can see that it is not really trivial. It is small but significant. So we can also extrapolate this to find the observables for the EUP black hole. So we have calculated 3 observables: magnification, time delay, and angular separation. These are the equations from the lens geometry here. And we can see that each of the factors here from the post-Newtonian approach, 1 plus alpha L square, in each of these observables that are contributing to the observables that are received from the EUP black hole. So that's about the EUP black hole. Next, we move on to the asymptotically flat black holes in Hornetsky theory. So the gravitational force given by Newton defines gravitational constant as g. Cavendish gave the the numerical value of g a decade later. And Einstein suggested that universe was finite and g exhibits a dependence with mass and the size of the universe. So g is not really a constant, but rather a dependent variable or dependent force kind of. So G accounts for the inertial forces still. So it was when Big Bang theory was confirmed through Hubble's observation later, and it was accepted that universe was indeed expanding like Einstein had predicted, and the probability of an infinite universe was established, the observable distance was still limited by the finiteness of the speed of light. We don't know anything that is more faster than the speed of light, but still it's finite. So the mass distribution and the size of the universe were changing with time. So hence the gravitational constant changes with time as well, meaning that the solution to this discrepancy, the possibility of G being a scalar field instead of being a constant. So that is the basis of what we call scalar tensor theory. So metric field contains gravity in the form of a tensor, consolidating the scalar field with a metric to give the scalar tensor theory. So one example inspired by the Lovelock theory is the Hornesky theory, which is a 4-dimensional space-time in which scalar field is incorporated as a new degree of freedom for the Lagrangian, and the second-order field equations of motions are obtained. So asymptotic flatness, according to this black hole, the gravitational field approaches zero at large distances, and asymptotically flat black holes mean that the black hole whose spacetime is static and spherically symmetric and reduces to the Schwarzschild spacetime when it is sufficiently far from the event horizon. So for this given black hole, we have the line element here with the H function defined as this, and K is the curvature parameter and mu is the mass, and it's integration constant that is analogous to mass. We have the lapse function here, and the deflection angle is given in terms of K and mu here. Then we have the refractive index defined as C over V again, and that gives the deflection angle to be this big number. And we have, of course, the reduction to Schwarzschild case. So this is plotted for vacuum case for varying mu, for constant mu and varying K. And we can see that K, when it has negative curvature, it is in the negative deflection, and with the positive curvature, it has positive deflection. And at higher values, it shows more and more deflection. Similarly, in plasma medium, we can see that for varying eta, which is the refractive index, we can see that it increases drastically. And for a more drastic increase in eta, it's even further higher. So the next is we talk about a Hornesky black hole itself instead of an asymptotic black hole in Hornesky theory. It's just a quick review of the Hornesky black hole. Is Lovelock theory of gravity, 4-dimensional space-time, scalar field, second-order field equations, and its applications are especially in cosmic acceleration and gravitational waves. So for Hornesky black holes, we will define f of r as this factor here, and this one is defined as gamma, which is a square of the square of charge of a regular Reisner-Nordstrom black hole. So the lapse function is given here, giving the deflection angle as this, and a refractive index in Hornesky theory is defined, and we find the deflection angle. And the results follow. The results follow here as gamma increases. We can see that deflection angle is quite increasing slowly, and with mu's increase, it is actually more prominent than of gamma. Then we have for plasma, it is the value of plasma is when it's small, it is almost the same here, though it's increasing, but for higher values, it's higher as well. And for increasing gamma, we see quite a small increase. Then we have the Reisner-Nordstrom black hole with higher order magnetic correction in Einstein nonlinear Maxwell fields. So Big Bang to black holes, singularity has been a matter of question. We don't know what happens at singularity. So we always try to come up with theories to supersede singularity. It hinders general relativity from being unified to other models of the universe, and the black hole solution without singularities presented by these two authors in this paper. So this was taken as the basics for this black hole. And this brings nonlinear electrodynamics into play to overlook the singularity. So the analytical black hole solution is much like the Born infield type corrections because the Maxwell field equations are similar. And then we have to the linear theory of Maxwell's theory in the weak field limit. This is an attempt to eliminate singularity as pointed out. So the governing equations are given here. And we can see the last factor here as the energy momentum tensor. And the next one here we can see that plays into the Lagrangian and it eventually comes up into this energy momentum tensor in terms of beta p. And finally, through the Einstein tensor, we can find the f of r for this black hole to be this equation. The Laplace function is shown here, and the weak deflection angle is quite big here. And we had to include till the order of 6 of impact parameter to see the effect of beta. Then we have a formalism for computing corrections to lensing for static spherically symmetric gravity theories because of this. So these corrections to the weak deflection limit is expanded as a Taylor series. So this one is actually a Keaton-Peters formalism. And then this formalism, as we can see, it expresses the line element as a series here. So this is given by Keaton and Peters. And comparing this with the initial metric, we can find that we can set as P equal to Pm, where small p is the charge, magnetic charge, and we can see that it agrees with the result that we obtained earlier to the second order of B. And this is actually a good method because we will be able to calculate observables through those coefficients that were defined. And we can find the same 3 observables that we found for the EUP black hole. Angular position, magnification, and time delay. Although angular position and magnification are beyond the scope of our current technology, time delay is still quite prominent. So the deflection angle of the ENM corrected RN black hole surrounded by massive particles is the big equation here to the 6th order of B again, impact parameter. And then we have for refractive index for the same black hole in plasma, we have the quantity here. I want to point out the uniqueness of these equations. We have the vacuum case and we have the plasma case, which are individually separated. So removing the effect of plasma will essentially give the vacuum case, and removing the effect of magnetic charge will give the case of the Schwarzschild case. So this is very flexible and adaptable to any other solution. So in the presence of dark matter, we again have a big solution, and this is again reducible to the initial cases. So the results now. So we have 2 different variations. One is beta and one is P. Beta is seen to have a very high deflection effect on deflection angle with a small increase itself, but after it has an effect, it kind of reduces quite slowly till it reaches at least even 10,000. But P, on the other hand, it shows a decreasing deflection. So the more the magnetic charge, lesser the deflection. And we have the effect due to massive particles here, with the showing to be lesser deflection, plasma showing to be more deflection, and we have dark matter showing to be a very widespread increasing deflection. So the effective, here we will talk about the shadow as well. Effect of magnetic charge on the radius of the shadow. It cannot be neutralized with regular matter. That is something to be pointed out about magnetic charge, unlike the electric charge in a conductive medium. So the Hamilton-Jacobi approach in the equatorial plane is given here with a critical impact parameter expressed as the linear momentum over energy, and critical impact parameter is shown here as the critical curve. And then we have the energy conservation equation with the dynamic potential having the equation here with the stability condition shown here. Together, assembling all of them, we can find the radius of the photon sphere and the radius of the black hole shadow with the distance of closest approach. So the magnetic charge tends to increase the curvature of the space-time, resulting in more photons being pulled into the black hole and decreasing the shadow of the radius. So with black hole spin, magnetic charge is found to create two distinct horizons, namely inner and outer horizons, stable and unstable photon orbits. So for a negligible charge, they are one and indistinguishable. So as the charge increases towards a critical value, the horizons become more and more prominent and we can see them more clearly. So the radius of the shadow of the black hole is defined here. And for a distant observer, for this black hole, we can find it to be this factor. So mathematically, if you have plotted here as this, and the ray tracing is done here. And then we have the shadow of the black hole with respect to the magnetic charge variation. And the constraint of the black hole charge here is the size depends on the black hole's physical charge, such as the electric charge, magnetic charge, etc. And the image of EHD is used to give the constraints on physical charges, and we can use that to constrain our theories. So we have here the allowed region and excluded region, and we have some this here. And then we have the constraints from EHD in the horizon scale. So the accretion disk is dynamic and spherical. The number of orbits are considered throughout the spherical accretion and not just the equatorial plane. So defining all of them together, yielding the red shift is this. And the infinitesimal proper distance is this, with the emissivity and the total observable flux defined as here. So this, when plotted with the intensity plot for a stereographic projection, we find the black hole to be here. And in terms of plasma, we can see that it is brightened up. You can see the difference in these two equations, in these two pictures. And next final black hole will be the asymptotic magnetically charged black hole. And this one again deals with an overlook of singularity. So again, we have black hole as an extreme gravity collapsing on itself. And singularity has been a mystery for over a century now. And non-singular black holes, instead of overlooking the singularity itself, is a prominent idea. And it was pioneered by Bardeen, so who suggests that alternative structures and mechanisms are at the center of a black hole, rather as a collapsed matter at its center. So this quantum effects may cause it to be a magnetically charged black hole. So that the previous black hole had a magnetic charge in it, around it, and this is a magnetically charged black hole, and that's how they are different. So this one yields the solution of its function, and the Laplace functions are given here, and then we have the ds here. In other black holes, we have r plus dr d phi. And in this black hole, it is interesting to notice that it has a r plus 3m term. And this m is actually dependent on q and beta. Finally, the weak deflection angle is given as this. And we have the variation here. One is the variation of L, which we can see is just one line. There is no absolute variation with any difference in L. Q, on the other hand, shows a decreased deflection. But as it increases, it's increasing towards the Schwarzschild case. And this is the effect of dark matter on the black hole, on the AMCNS black hole. And then we have the constraints on the EHD, again, being averaged over Keck and mass-to-distance ratios. Then finally, we have the intensity plots for the stereographic projections. We can see that it is very, very small, but still very, very prominent. We can see the middle picture appears to be smaller than the bigger one if we take a closer look, but it is not really evident when we see overall. And this is another aspect of it, shadow radius seen here. So to conclude, there are 5 different black holes were studied under various conditions, and each individual factor, namely vacuum, massive particles, plasma medium, and dark matter, they showed a distinct consequence on each of the deflection angle on each of the black hole, and they were prominent enough to differentiate one effect or a black hole from the other. So basically, if we look at a black hole and if we see what black hole it is, and if we can have a list of parameters that can define them, we can pick out which one it could be, or what parameters it could have. So with similar behaviors being distinguishable at a particular range. So all the calculations were done with relatively lesser assumptions and approximations, especially mathematically, and suggesting that these theories are built, the theories that are built from these results could be more accurate for future understanding. So this research will be followed by further contributions in gravitational lensing, along with the study of accretion and how it affects other gravity-related entities. So scope of this research is the astrophysical parameter uncertainty, which dominates gravity theories and parameter uncertainty, and underlining the importance of understanding the accretion model if Event Horizon Telescope is used to successfully test the theories of gravity. So all we have to do is keep giving theories enough, accurate enough theories, enough for observational astrophysicists to work. So recent theoretical developments allow computational inexpensive frameworks to produce high resolution images and study how photon ring based experiments could test GR in a fairly astro independent way, because we don't know what we can expect. So the future looks bright. Additional telescopes will improve image fidelity. This may allow us to measure the shadow asymmetry, which is essentially dynamic. And the first image of M87 can be used to measure shadow radius within 17% error bar, can be used to constrain modified gravity theory of black holes. And these constraints are about 500 times more stringent than solar system tests, also comparable to LIGO and Virgo constraints. So we aim to perform better tests in the future. Thank you for listening, and I would like to ask you for questions.
Thank you, Yashmitha.
Thank you very much.
Very nice talk, very comprehensive. Thank you very much. Do we have questions from the audience to Yashmitha? We have participants here, and each participant can ask a question. I mean, everybody here in the list. We have some 19 people, not only the committee members.
I want to ask a question.
Yes,
Do you hear me?
Go ahead. I mean, I'm not able to hear. Go ahead.
Okay. Please pass your slides, the last graph, the last plot. Yes.
Which one?
I want to understand why did you get a sharp maximum instead of the smooth maximum about B equal to 5?
Sharp maximum, sorry, can you repeat again?
Why did you get maximum? I want to understand about B equal 5.
Okay, so the intensity plot is actually with respect to the black hole here. So we can see that the central region is dark, which shows the minimum here that's coming here. And when it peaks up here, it just means that the maximum peaks here when the shadow is at maximum intensity. So that's the peak. And as it goes towards the border outside, we can see that it slowly reduces here, falls down smoothly.
Okay, thank you.
Other questions from the audience?
So, can I ask a question?
Yes, Hojam.
Okay. Actually, in some part of your presentation, you were talking about dark matter and its effect in the lensing of light.
Yes.
So you meant light has interaction with dark matter?
Yes. Yes, Hojam.
Are you sure about?
It's gravitational, dark matter's gravitational effects on the light trajectories is more appropriate, I think.
So you know exactly how physical community, they realize there is dark matter.
Yes.
So what is the evidence there? Very, very strong evidence of dark matter. Do you know what is that?
We have the missing mass problem that the universe should be weighing so much, but only 5% is observable universe.
Yeah, that is what I say. I mean, you know what is the evidence why we think there is a dark matter from where it started from. If dark matter has interaction with light, why they couldn't discover it directly so far?
Because we have only evidences, we do not really have any solid proof that it exists. We can see it manifesting in clusters and dark halos and even in lensing, but we don't really see the physical evidence being present.
Okay, so your answer is that dark matter has effect or interact with light.
Yes.
Thank you.
Can I ask another question?
Sure, Hocam.
Go ahead,
Okay.
please. Please.
Okay, thank you. Could you say about your calculation? I think you use a mathematical program. This is a special program, Özgün package, I think. Could you say something about it, about this program? Maybe
Computer code.
So we start off with defining the metric for the black hole, and then we proceed to calculate the Christoffel symbols for the given line element, and then we calculate the Ricci scalar from the Christoffel symbols, and then we calculate the Gaussian curvature, and for the given area of the ds, we have k times ds, we integrate it over the limits that were specified, and we find the deflection angle. So the package is the same as what we do it mathematically step by step, but just that it has it's not limited to a certain number of terms. We can limit it if we want, but it's not limited to a certain number of order of magnitude of impact parameter.
Okay, thank you.
Any other questions from the audience? From the committee members, I mean, they are also included. Yashmitha, can I have a, oh, I'm sorry. Yeah, please go ahead. Hocam, you go ahead.
Hocam, I can't
we don't
hear you.
Huh.
Could you unmute, Hocam?
Could you unmute yourself? Osman Hocam, we don't hear you, unfortunately. We are not able to hear you.
Okay, sorry.
Okay, you go ahead, please. Yeah.
Okay. So, Yashmitha, you know I am from the chemistry department.
Yes, Hocam.
And after getting your PhD degree, you will be eligible to teach in a university as an assistant professor. And perhaps one day you will teach chemistry students. You will teach physics to chemistry students. Physics 101, perhaps optics, I don't know. So my questions will be so basic questions that, and I will expect from you to answer these questions by using very simple language, I mean, without referring to any questions, etc. So I wonder about the size of a black hole. Okay. Is the point mass? You said that matter collapses into a single point, and it pulls everything into this point. So in that case, a black hole is it something like a point mass having a huge amount of mass with no volume. So how shall we visualize or imagine a black hole?
Hojam, the best way that I have learned to imagine a black hole is like putting a ball in a bed sheet. You know, if there is a flat bed sheet, we imagine that as a flat space time. When we put a ball on the bed sheet curves. So when the bed sheet curves, it curves depending on the mass of the ball that we put there. So higher the mass, more is the curvature. So black hole is a point of extreme gravity and mass. So meaning that its gravity is so much that it's not able to, it's collapsing on itself. So it's going deeper and deeper into the space-time fabric, creating a funnel-like shape. So that's how we imagine black holes to be, at least mathematically. So physically or observationally, we are seeing the shadow. That's what we call the appearance of a black hole instead of a black hole itself, because beyond the event horizon, we cannot see anything so far. And that's why studying black holes is important, because we have access to new knowledge that we can find.
I see. So still, in terms of chemical fundamental particles, so you, from time to time, you mentioned about protons.
Yes.
But as chemists, you know, we describe matter with, with atoms, including protons, neutrons, and electrons. Yes. So during this collapse of matter, so what happens to those protons, neutrons, and electrons? Do they approach each other? They come into a touching distance? So they are converted to another particle? Is there any study on this, or any theories perhaps to explain the curiosity of chemists?
I'm thinking, Hojam, maybe it's more like to do with how matter collapses on itself. So I actually never thought about this, because we think black hole as a quantum entity in itself. We don't distinguish between like protons and electrons in that quantum level. And I don't know, it's probably compressed into that one small space, and like when it collapses onto itself, it's compressing on itself. So the extreme conditions, we cannot be sure of what happens. There are multiple theories on what lies inside a black hole itself. So if you saw the first slide, we spoke about EUP black holes and the information paradox. So according to the information paradox, a black hole takes in information and sends it into its center, which never comes out. So that cannot be possible according to quantum mechanics. Information cannot be lost like that. But rather, so Hawking proposed that it should rather be dissipated. So protons and electrons may not survive a black hole, but their signatures may be preserved as quantum fluctuations around a black hole. That's all. That's how I understand it as.
Okay. One last question. You said on one page of your thesis and in your presentation as well, gravity is the least powerful among the fundamental forces in our universe.
Yes.
So what other forces we are talking about then, stronger than gravity?
We have electromagnetic force, and we have strong nuclear force, and then we have weak nuclear force.
Kerem hocam sağ ol, var ol. Ne güzel bir yol gösterdin. Ben hiç aklımda yoktu o yol. Ama Gizem ablası Uğur'a da yardımcı olacak, bir gösterecek etrafı.
Thank you, Yashmitha.
Welcome, hocam.
From my side.
I think Urmush hocam had a question.
So our chair is now busy. So if you have any question, other audience or other participants are welcome. Yes, Yashmitha, you didn't answer this question. What software you use to plot your figures?
Initially, I started learning in Maple Hojam, and then I shifted to Mathematica for the last 3 black holes.
So now you use Mathematica for the shadow of black holes.
Yes. Shadow, sometimes I prefer it in Python because sometimes I'm more comfortable with Python. But Mathematica is mostly is used for the main calculations of deflection angle.
Okay, very good. So I remember in our previous meeting, I asked you about Gauss-Bonnet theorem. Now I see in your thesis, you gave a lot of information. That's great. So from a third-party point of view, when I look at the thesis, it is comprehensive and it's understandable. So I congratulate you for this useful information you added into your thesis. I hope this thesis will be used also by our other students for further development of the theory. So of course, I would be very happy I'm not a physicist, but somebody who is into physics. So that you invented a method like that Gauss-Bonnet method or theorem method, let's say, finding weak lensing. But even you didn't create it, but you used it in a proper way. So I am very happy. So congratulate you. I think you did a good job, especially the paper you published. They also the proof of your job is qualified. So I congratulate you and your supervisor both in this week.
Thank you, John. Thank you so much.
I'm sorry for the phone call. I mean, it was something urgent and I had to pick it up.
No.
Let's go ahead. I mean, was there anyone asking question, Yashmitha?
No, John.
Oh, I'm sorry. Yashmitha, I was just wondering about one point. Can I have a question?
Sure.
So you were discussing the case of this singularity. You were trying to prevent this.
Ojam, I'm sorry, your voice is breaking off. Can you repeat it again?
I'm saying that you were trying to prevent the black hole singularity at some point.
Yes.
Actually, don't we expect to have a singularity? I mean, what do we want by preventing the singularity or the singularity? What do we expect from the system? I was just wondering.
So if we exclude singularity, we can avoid the case of extreme gravity or extreme density. Like everything in our universe is finite. Even the speed of light that we know is the fastest, but it's still finite. So if we have something finite to work with, we can remove that assumption of maybe it will work like this in a second, or maybe this is the case. So finiteness we are aiming for.
Okay, I got the point. Okay, thank you. Is there any other question from the guests, from the audience? Maybe we committee members stay and the other friends or other guests or audience members can leave, because I think we should continue kind of examination.
Yes, Hocam, you are right. So I can remove all other.
Okay, Ali. Yeah, that's better.